Good afternoon. My name is Abel Galaz, and I will be presenting the Lacaz-Voltaire's predator versus prey model. The relationship between a predator and his prey has been involved in our life since the dawn of time. Most animals found in the wild tend to have an eat or be eaten mindset. That's the reason why they're capable of surviving. A predator is considered an animal who lives by killing and eating other animals, such as a wolf or a coyote, while a prey is considered as an animal that is hunted by an animal for food, such as a rabbit or a squirrel. The predator's prey analogy has been seen and used in all kinds of ways, that being sometimes not even related to animals themselves. But in this case, let's dive down to the history behind Lacaz-Voltaire equation. The story behind the Lacaz-Voltaire equation begins with Alfred J. Lagda. Born on March 2nd in 1880 in Lviv, Ukraine, he initially proposed the theory in 1910. Lagda grew a great interest in the application of mathematics to biology. But he didn't receive much recognition in the starting time of research. It wasn't until Raymond Pearl, a biostatistician from Johns Hopkins University, who noticed and looked into Lagda's work. Being impressed, Pearl invited Lagda to stop by his university to publish his work into a book. This collaboration led to the creating of the original Predator vs. Prey. In 1920, Lagda furthered his development of the equation to an organic system, using plants and animals as examples. But soon after, in 1925, he then developed the version of the equation we all know today, using animals. In the late 1926, Vito Voltaire would come into play. Understanding Lagda's work, he was thrilled and excited to learn about the oscillations created by the result in the interactions of the predator versus prey. But during this time, Voltaire proposed a differential equation model that will help further and explain the predator versus prey. Once their ideas were put into play, they came up with the Lagda-Voltaire model equation. That equation helped develop graphs such as the bottom left one comparing the two equations. One graph, the blue, is for fox while the red is for rabbit. When one goes up, the other soon after goes up with it. If one comes down, the other will soon after come down. The oscillations on the graph on the right help describe the predator versus prey cycles, which are based off the feeding relations between two species. If the prey species rapidly multiplies, soon afterwards, the number of predators increases as well. If the predators eventually eat so many prey, the population of the prey will go down, which will cause the population of predators to go down, which then will repeat the cycle once more. Looking into the equation itself, it consists of a few key components. The X representing the prey's population, the Y representing the predator's population, T representing time. Alpha is considered the growth rate of the prey. Beta is the rate at which the prey are murdered by the predators. Y is the rate at which predators die at. Change is at the rate of how much predators are increasing due to consumption of the prey. DXCT is the instantaneous growth rate of the prey, which is what's graphed. DYDT is the instantaneous growth rate of the predator, and C is the constant. Now, solving the equation is pretty simple. You want to begin by separating the equation into the X and Y, which is what the Lagda-Voltaire equation is. And then you recombine the equation by dividing the rate population over the rate population of predator over the prey. Once that, you want to factor out the negative y on the numerator on the right side. The next step would be to eliminate the fraction by cross multiplying. Once then, you want to divide both sides by x and y. That way you're separating the x and y in order to set up the integration. Once ready, you want to subtract the left-hand side by the right-hand side in order to set the equation equal to 0. Lastly, you want to integrate both sides of the equation, which will simplify into beta y plus change x minus alpha ln y minus y ln x equals c. This equation helps demonstrate the potential outcomes when predators and prey meet. Looking into the increase and decreasing population rate of the prey, when increasing the at the graph, when increasing the population rate of the predator population will follow close along. This happens due to the increase in meals for the predators, which will cause an increase in population. Now, looking when decreasing the population rate of the prey, the population of the predators will also decrease, which is caused by the scarcity of the food for the predators, which will potentially lead them to extinction if it comes to a too low of a number. To conclude, the predator versus prey theory is involved in all through our lives in nature. Whether it's seen as methods to describe nature, it can be very much represented in other aspects of life. The logical Volterra theory is an example of how mathematicians can relate math to nature. Thank you very much.